In the last module, we looked at the different user interface technologies and how they function. Now we will move on to the second functional group and see how the output products of a user interface can be collected, stored, and/or treated on-site. The functional group Collection and Storage/Treatment describes the ways of collecting, storing, and sometimes treating the products generated at the user interface. The treatment provided by these technologies is often a function of storage and is usually passive without requiring energy input. Products that emanate from these technologies often require subsequent treatment before use or disposal. There is quite a wide range of technologies which belong to this functional group. In order to present them in manageable packages, I split them up into 3 modules. In this module, I will talk about technologies in which a single pit is used. Then, I will present the options which rely on 2 alternating pits to function. And third, we will look at anaerobic technologies which are not based on pits. So, let's start with the first module. I will first present the difference between a single pit and a single ventilated improved pit. Then I am going to explain how the ventilation functions and why it can be an advantage to install a ventilation pipe with a pit. In the end, I will show some key considerations for a good pit design. The single pit is one of the most widely used sanitation technologies. It consists of a hole in the ground which is usually 3 or more meters deep. It normally has a lining to stabilize the walls of the pit. At least the top 20 to 40 centimeters should be lined with a support ring made of bricks or blocks. The user interface can then be placed on top of it. I will give you some more details about pit lining a little bit later. The single pit is a simple technology which is most suited to rural areas and can be at very low cost depending on the materials used and the depth of excavation. However, emptying costs may be quite high and the sludge needs to be further treated. This has to be considered when choosing this option. A major disadvantage of single pits is that the emptied sludge is still very pathogenic and leachate can contaminate groundwater resources. Also, odors are normally noticeable, and flies hatching in the pit can be a vector for disease transmission. As we have seen for the user interface, the different technologies have different input and output products. This also applies to each technology from the other functional groups, including collection and storage. If we take the example of the single pit, the input products can be excreta, black water, or feces, usually mixed either with anal cleansing water or dry cleansing materials. Remember that those are the output products of the different user interface options. Obviously, several user interface technologies are compatible with this technology here, because several different input products are possible here. On the output side, we have fecal sludge, which needs to be transported for further treatment. For the following technologies, I won't give such a detailed presentation of the inputs and outputs anymore, because the principle remains the same. But if you are interested about possible inputs or outputs of a specific technology, you may look it up on the corresponding page in the compendium. When designing a sanitation system, it can be very helpful to look at the input and output products of a technology to see which options can be linked to it before or after. Single pits can be improved by installing a ventilation pipe with a diameter of at least 11 centimeters. They are then called Ventilated Improved Pits or VIP. But why is the ventilation an improvement? Of course, it can eliminate odors, but it also has another important function. But let's first look at how the ventilation works. The main driver that helps to ventilate a pit is actually the wind. Wind passing over the top of a ventilation pipe creates a suction pressure within the pipe and induces an air circulation. If the vent pipe is well fitted and the edges of the pit are airtight, the air is drawn through the user interface into the pit, moves up inside the vent pipe, and escapes into the atmosphere. For an effective ventilation, the top of the pipe should extend at least 30 centimeters over the roof of the superstructure. The vent works best in windy areas, but where there is little wind, its effectiveness can be improved by painting the pipe black and exposing it to the sun. The heat difference between the cool pit and the warm vent creates an updraft that pulls the air out of the pit. Besides removing odors, another beneficial effect is that flies that hatch in the pit are attracted to the light at the top of the ventilation pipe. With a semi-dark superstructure, flies fly toward the light in the pipe. A fly screen or mesh at the top of the pipe traps them and prevents them from escaping. The attraction for flies from the outside is also minimized because odors are allowed to escape. A good ventilation effectively prevents odors and is able to reduce the fly problem and the spread of diseases they may carry. The ventilation is not that easy to construct properly. However, a design like the one here is probably a bit exaggerated. Something like the one over here with a good fly screen is normally sufficient. The VIP is a low-cost option, although slightly more expensive than a simple pit. Other advantages and disadvantages are the same as for the simple pit. Now let's look at some general design considerations for single pits. Pits may be circular or rectangular in plan, as shown on this image. Round pits are more suitable because the earth pressure is evenly distributed, creating a natural arching effect. Rectangular pits have a tendency to collapse. Typically, a pit is at least 3 meters deep and 1 meter in diameter. Especially if the pit is to be reused, its walls should be lined. This prevents the pit from collapsing during emptying. Pit lining materials can include brick, rot-resistant timber, concrete or stones. The lining of the upper edge of the pit can be built in the so-called corbelled brickwork technique, as shown here. This design allows to use a smaller diameter slab and can save some costs. The bottom of the pit should remain unlined to allow for the infiltration of liquids out of the pit. Permeable sidewalls can accelerate deleaching. To protect the groundwater, sometimes watertight or sealed pits are built, but this can be very expensive. To prevent groundwater contamination, the bottom of the pit should be at least 2 meters above the groundwater level. A minimum horizontal distance of 30 meters between a pit and a water source is normally recommended to limit exposure to microbial contamination. But these values depend on the soil type, moisture, and other environmental factors. The pit volume should be designed based on the number of users, the design life or desired filling time, and the local sludge accumulation rate. The sludge accumulation rate depends on several factors, including the infiltration capacity of the soil, the biodegradability of dry cleansing materials, and the water use. It is typically in the order of magnitude of 40 to 90 liters per capita per year. Single pits are a simple technology which can be very appropriate, particularly in rural areas with a low risk of groundwater pollution. Single pits should not be used where the groundwater table is high, or in areas that are frequently flooded or have rocky soils. They are not suitable for dense urban areas, particularly because emptying can pose serious problems and health risks. The use of a vent pipe in a VIP adds comfort and reduces flies, but needs to be carefully designed to function properly. In the next module, we are going to look at the technologies that use two pits.